Okay, so today we're going to look at an introduction to the pH scale. So we've already kind of worked with this a little bit in class, and we know that pH scale is a scale from 1 to 14 or 0 in some cases, where below 7 is acid and above 7 is basic or alkaline, and 7 is neutral. So we're going to start to look and see how the pH scale was actually developed. And why is it a 0 to 14 scale? What do those numbers mean? Okay, so if we remember, most of the time when we're talking about an acid and base, we're dealing with a solution that's in water. But water is one of those special things. Water is amphoteric, so it can act both as an acid or a base. Water also does a lot of other special things. One of them is it undergoes self-ionization. All the other time we've seen ions previously in this class is when we've added ionic compounds to water, they ionize. But water actually ionizes itself. So what does that look like? Okay, so if we remember that water self-ionizes and water is amphoteric, let's pretend like this water molecule over here is the base. So let's write B for base. Sorry, I'm using my mouse pad for this. And this water molecule is the acid. Okay, so we have a base, we have an acid. Well, we know that bases do what? Bases accept protons, and acids donate them. So the first water molecule is going to accept a proton, so it's going to be H3O plus. And the second water molecule, since it's acting as the acid, is going to donate the proton to be OH minus. So this reaction water undergoes, and actually all water have concentrations of hydronium and hydroxide in them because water undergoes this self-ionization process. Now, they aren't strong concentrations, but in every water supply, both of these ions are present because water does this. Water can act as both an acid and base. So when you have water mixing, some of the molecules are going to go into hydronium, and some of them are going to be hydroxide. So when water does this, and we want to find out at what rate water does this. So if we look back at the chemical reaction, does most of the water that you have, does it exist as H2O, or is most of the water, maybe, let's say it's H3O or OH minus? Well, chemists have measured this, and here's what they've come up with. There's a value called Kw. Kw is called the ion product constant for water. So ion product is telling us that we're dealing with ions that are the products, and this is a constant value for water. Acids and bases also have they have Kas and Kbs to find out how much they break into their ions, but for any time you see a Kw, you know you're dealing with water. So the W helps signify that we are dealing with water here. And here's the equation that we have. Kw is equal to the concentration of hydronium times the concentration of hydroxide. At 25 degrees Celsius, these concentrations have been measured. And let's see, and they are the following. So at 25 degrees Celsius, the concentration of hydronium in water has been measured to be 1.0 times 10 to the negative 7th molar. The concentration of hydroxide at 25 degrees Celsius in water, in pure water, has been found to be 1.0 times 10 to the negative 7th molar. So what do we notice about these? Well, we notice that they are the same, right? So we know that water is neutral, right? When we tested it with pH paper, we found that water gave us a pH of 7. And here's why water is neutral. Well, we have the same amount of hydronium as we do hydroxide. And we know an acid increases the amount of hydronium present, and a base increases the amount of hydroxide present. But in water at 25 degrees Celsius, we notice that they're the same amounts. We have the same amount of hydronium as we do hydroxide, and therefore water is said to be neutral, which confirms what we know. Well, we also know that Kw is a constant, so we can find what Kw is. So let's plug these values back into this equation, and let's see if we can't calculate Kw. So Kw is equal to the concentration of hydronium. So at 25 degrees Celsius, our concentration is 1.0 times 10 to the negative 7th, multiplied by the concentration of hydroxide, 1.0 times 10 to the negative 7th. When we do this, Kw is equal, and if you remember rules of exponents, when you multiply two scientific numbers together, you can add the exponents to give you your new exponent. Kw is said to equal 1.0 times 10 to the negative 14th. What this number tells us is the likelihood of water to ionize. So if we go back to our equation, a chemical equation that has a high or a large K value, this is a very small K, right? If we think of 1.0 times 10 to the 14th, well, that is 0.0 with 13 zeros, right, before 1. Very small number. So if we look at our equation, what that tells us is there's not a lot of ions in water. Okay? When water adds to itself, there's not a lot of hydronium, there's not a lot of hydroxide. It doesn't go this way. So if we were to accurately write this double arrow, what we would really see is the top arrow would be really, really small, and the bottom arrow would be really large. So if you have pure water, almost all of it, our Kw with it being so small, tells us that almost all of our water is going to be in H2O. There is not going to be hardly any that goes to the ion products. So Kw is equal to 1.0 times 10 to the 14th. Since we know this is a constant, Kw is always equal to this value. Now, your concentration of hydroxide and hydronium can change, but your Kw does not change. So let's see what happens. In an acid, we know that the concentration of hydronium is greater than the concentration of the OH. So let's see an example here. A solution has a hydronium concentration of 1.0 times 10 to the negative third molar. Let's find the concentration of the OH. After we have these, let's look at them, compare them, and state, is this solution basic, neutral, or acidic? So from the previous slide, we know that Kw is equal to the concentration of H3O times the concentration of OH. So we can plug and solve. Kw is always a constant 1.0 times 10 to the negative 14th. And that is going to equal, we're given our concentration of H3O, 1.0 times 10 to the negative third. We are trying to solve for the concentration of OH. So let's leave that. Well, this is an easy thing to solve for, right? We divide both sides by 1.0 times 10 to the negative third over 1.0 times 10 to the negative third. Cancel out. If you remember, again, rules of exponents, if you are dividing by exponents, you subtract them, so we have negative 14 minus negative 3. So the concentration of our OH in this solution is negative 14 minus a negative 3 is equal to a negative, negative 11. Sorry. So the concentration of our OH is 1.0 times 10 to the negative 11th molar. So let's look at this. Is this solution acidic or basic or neutral? Our H3O concentration was 1.0 times 10 to the negative third molar. Our OH concentration was 1.0 times 10 to the negative 11th molar. Well, our hydronium concentration is much larger than this by a factor of what? 10 to the 8th. By a factor of 10 to the 8th, we have more concentration of hydronium than we do have hydroxide. So this is a acidic solution. So where this Kw comes in handy, and knowing the concentrations of hydronium and hydroxide, is we can find out if a solution is acidic, basic, or neutral just by knowing the concentrations of H3O and OH minuses. So we set it up in this equation right here. Kw is equal to H3O plus times OH minus. Okay, here's two practice problems for us. So what I want you to do is find the OH, the concentration of the hydroxide, if the hydronium concentrations are as follows. So if you want to practice this, go ahead and pause the video right here. Work these two out. Remember to use the equation this equation. Kw is equal to the concentration of hydronium times the concentration of hydroxide. So go ahead and plug in these hydronium concentrations. We know Kw is 1.0 times 10 to the negative 14, and solve for hydroxide. So if you want to go ahead and pause the video right now and solve those, when you unpause, I'll go ahead and have the answers ready for you. Okay, so the first one, when we solve for the OH, our OH concentration, when our hydronium concentration is 7.5 times 10 to the negative fifth, we have an OH concentration of 1.3 times 10 to the negative 10th molar. So if we compare these two values, 7.5 times 10 to the negative fifth, 1.3 times 10 to the negative 10th, this is a much smaller number by a magnitude of 10 to the 5. So this first solution should be acidic. Let's look at the second solution. When we solve for our OH concentration in the second solution, we will find that the OH concentration is equal to 6.7 times 10 to the negative 6th molar. When we compare these two concentrations, we find what? The OH concentration is larger. 6.7 times 10 to the negative 6th is a higher concentration than times 10 to the negative 9th. This is a basic solution. Okay, so there's our intro into hydronium and hydroxide concentration and Kw. Go ahead and try these. Hopefully you did okay trying those problems. If not, talk to me on class on Monday and we can try to get it squared away.